What could be a better estimate than a left endpoint Riemann sum or a right endpoint Riemann sum? In many cases, the midpoint Riemann sum could provide this better estimate. Let's look at a very famous algebra function, the square root of x. And we're going to look at this function on the interval from 1 to 3. And the function is actually concave down and increasing. And we're trying to fit 4 rectangles of equal width to estimate the area underneath this continuous function. Now we're trying to get the midpoint here. So I'm going to try to fit 4 rectangles in here. And then we draw the horizontal line or the top edge of the rectangle by crossing the midpoint. So the midpoint's down there, and that is actually what we call our first midpoint, x sub 1. Notice the rectangle will actually overestimate, then underestimate. I'm going to do the same thing over here. I need to draw the midpoint called x sub 2. And the horizontal line that represents the top of that rectangle will cross the midpoint at the output of the function value. Right here is x sub 3. Once again, we draw the rectangle. So on the left edge of the rectangle seems to be overestimating, and the right edge of the rectangle seems to be underestimating. Now, how do we write our Riemann sum? We want a midpoint Riemann sum. We always start with delta x. Delta x is just a formula. And our delta x is 1/2. Now for the midpoint, there's really a good strategy, and that is we need to know what a is. So our very first midpoint is given by a plus half the width of delta x, or half of delta x. A is 1 in our case, and half of a half is just 1/4. So our very first midpoint is 5/4. Once you find the first midpoint, it is much easier to find the second midpoint. The second midpoint is actually the first midpoint plus delta x. And the next midpoint is actually the previous midpoint plus delta x. And finally, the last midpoint is the previous midpoint plus delta x. We're ready to find our midpoint Riemann sum. You may have realized there's a pattern to this. The common denominator is just 4. And this number here is our estimate of the area underneath the curve. In many mathematical models, the sum is really not always representing area. For instance, let's look at the velocity graph below. Notice the car has hit the brakes, and it hit the brakes over 6 seconds. So imagine the car braking. That means the velocity must be decreasing until the car comes to a stop. We can actually use this graph to estimate the distance traveled by the car while the brakes were applied for 6 seconds. My hint to you is that use n equals 6 rectangles and pay close attention to the units of measure. And so let me give you more of a hint here. You could use the left endpoint, midpoint, or right endpoint Riemann sum. Whatever you decide to use, your Riemann sum will look something like this. Now pay close attention to the units of measure. Notice the velocity is measured in feet per second, and time is measured in seconds. So if you do your unit analysis, you're going to realize the final answer is measured in feet. Here's another example where your estimate here has nothing to do with area. So depending on what you're analyzing or what your model is trying to indicate, you have to pay close attention to what these rectangles really mean. For this particular example, if I wanted to estimate this, I would use a midpoint Riemann sum, and I would only use specifically 4 rectangles. I'll leave it up to you to perform this calculation, but what's really intriguing is that our estimations really have nothing to do with area. It's just a geometric representation of a number. So let's look at it from a unit standpoint or unit analysis standpoint. We can see that the Riemann sum will look something like this. And if we analyze the units of measure, we notice we have millions of barrels over years, or per year, times a measurement of time. And our measurement of time is in years. Once again, notice the unit analysis. Notice you're left with the Riemann sum that is measured in millions of barrels. How do we get better estimates of the number between the function and the x-axis? Should we decrease the number of rectangles or increase the number of rectangles? How do we get a precise number or even an exact number? Let's dive into a Desmos activity to find out. To better estimate the area between a function and the x-axis, should we increase the number of rectangles or decrease the number of rectangles? And is this really an area number? Let's begin with this polynomial here. What you're seeing is a one rectangle estimation of the number that is represented by the space between the function and the x-axis. To get a better estimate, we're going to increase the number of rectangles. Here's an estimate using 10 rectangles. Notice there are some gaps in between the function and the rectangles. In some cases we overestimate, in some cases we underestimate. But if we increase the number of rectangles slowly, notice 13 rectangles make a pretty big difference from 10 rectangles. And we get a better and better estimate as we increase the number of rectangles. Notice there's less and less space, less and less gaps at 60 rectangles. What's better than 60 rectangles? Why don't we try 100 rectangles? What's better than 100 rectangles? How about 160 rectangles? If you look closely, you could still see the corners of the rectangles that are lying below and over the function. So why stop at 260 rectangles? What's a better estimate than 260 rectangles? How about 500 rectangles? But what would be better than 500 rectangles? You could see that we are using a fundamental process of differential calculus. And that fundamental process is actually using the limit. With the use of a limit, we could actually find the exact number between the function and the x-axis. That leads us to this new definition. Increasing the numbers of rectangles to infinity. We use the process of a limit and we get the following new definition. Suppose a continuous function f of x is defined on a closed interval a to b, which is divided into n subintervals of equal width called delta x. The total accumulation number between the function and the x-axis is represented by this limit. And this limit is actually the limit of a Riemann sum as n goes to infinity. That means we take the limit of a Riemann sum, we let n go to an infinite number of rectangles. This accumulation number a could be positive, negative, or 0. And the reason for that is this function could take on positive or negative values. This definition is vital to many different applications of integral calculus. When the limit does exist, we will actually morph the mathematical writing to include an elongated S, the domain from A to B, and the differential dx.